In this screencast, we are going to talk about how to classify monosaccharides. We are also going to talk about Haworth projections. So when we go through and classify monosaccharides, there's a few questions that we need to ask ourselves. One is the monosaccharide an aldose, which means it contains an aldehyde functional group, or a ketose, which means it contains a ketone functional group. And then we need to ask ourselves how many carbons are present. Now, when we go through and do this, I want us to do two examples here. This example here contains an aldehyde functional group. So that means it would be classified as an aldose, and it has 1, 2, 3, 4, 5, 6. And so we would say, hey, look, that's an aldohexose. Then this over here would be functional, has a functional group that's a ketone, and so it would be classified as a ketose, and it would have 1, 2, 3, 4, 5 carbons, and so it would be a ketopentose. And that's how we would go through and classify it. If these carbohydrates have 3 carbon atoms, they're a triose, 4 is a tetrose, 5 is a pentose, and 6 is a hexose. Now, the simplest carbohydrates are monosaccharides, and they are going to have that aldehyde right here, or the ketone functional group. One of the things to be aware of is that most monosaccharides are aldoses. Not all, but most. And almost all natural monosaccharides belong to the D series. So that means they're going to be the D monosaccharides. So let's look at a family of D-aldoses. So this is a family of D-aldoses. It starts with D-glyceraldehyde, which is the smallest monosaccharide with a chiral carbon. And then notice, right, the bottom chiral carbon of each compound is directed to the right because these are all the D monosaccharides. And so when we look at this to classify it, all right, we're looking here, 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 and here. Okay, and you can also see where they're classified based on the number of carbons. So glyceraldehyde is an aldotriose, the aldotetroses are here, the aldopentoses are here, and the aldohexoses are here. The other half, which would be the enantiomers, are not shown. So we're just looking at the D enantiomers here. Most monosaccharides are called sugars because they taste sweet. And the amount of sweetness varies, as shown here. Fructose is the sweetest among the common sugars here. and it's about 73% sweeter than sucrose, which is table sugar. So sucrose here is table sugar. All carbohydrates are solids at room temperature. And because they have so many OH groups present, they are extremely water soluble. In the body, this solubility allows carbohydrates to be transported rapidly into the circulatory system. And so that's one of the many reasons that carbohydrates are a pretty rapid energy source. Now, so far, we have represented the monosaccharides as open chain polyhydroxy aldehydes and ketones. And these representations are useful in discussing the structural features and the stereochemistry, but aldehydes and ketones will react to form hemiacetals and hemiketals. And when they do this, they form a cyclic molecule. And so what we know is that all monosaccharides with at least 5 carbon atoms exist predominantly as cyclic hemiketals and hemiacetals. Now, we represent these using Haworth structures, and these are just a method of depicting 3D carbohydrate structure. And so when we look at this, particularly with the Haworth projections, what you see here is the CH2OH is at the top. There's an oxygen here, and this oxygen is part of the ring. Then you can see the hydroxy groups here. When we view this, it's like this is coming out towards us, and so that's why it's darkened, is that we're trying to represent that three-dimensional structure. In this instance, both of these are hemiacetals. And I just want to remind you that a hemiacetal functional group looks like a carbon with an OH and a OR. So it's a carbon that is bonded here, right, to an OR group, and then the OH right here. And so that's what we're looking at there for that hemiacetal group. So over here, it's a carbon that's bonded to the OR and the OH. If you look at all the other OH groups, none of them are directly have a carbon that's bonded to an oxygen, right? So there's not like an OH over here, there's another carbon. So highlighted in blue there are those hemiacetal groups for you. Now, let's talk about how we go from the straight chain to the cyclic molecule. When we do this, it's helpful to bend the molecule over and around like this. So this is glucose, and the functional groups here are in closer proximity. I also want you to notice the numbering, 1, 2, 3, 4, 5, 6. What happens here is that this alcohol will form a bond between the oxygen and the carbon, and then we will also form an OH here where there is the carbonyl group. When this happens, you end up with a carbon that's bonded to two oxygens right here, and this is called the anomeric carbon. So the anomeric carbon can be kind of defined as either the acetal, ketal, hemiacetal, or hemiketal carbon, okay? And that does give rise to two stereoisomers. Another way to identify it is it's a carbon that's connected directly to two oxygen atoms. Now, one of the things that we notice is once we form a ring, we end up with two different stereoisomers, and these are called anomers. Anomers are just stereoisomers that differ in the 3D arrangement of groups at that anomeric carbon. So these differ in the 3D arrangement of the groups at the anomeric carbon. So you identify the anomeric carbon, and then if the OH is up, that's a beta hydroxy group, and we name that as beta D-glucose. And then if the OH is down, that's an alpha hydroxy group, and we name that as alpha D-glucose. The D-glucose part just comes from the fact that this molecule is D-glucose. Okay, and so the alpha anomer is the one where the OH is pointing down, and the beta anomer is the one where the OH is pointing up. Now, the way that I remember this is alpha is down and beta is up. And when we look at consonants and vowels, alpha starts with A, and that's a vowel, and then this is a consonant, which is D, and then beta starts with a consonant, and then up starts with a vowel. And you'll notice that you always have a vowel and a consonant. You never have two consonants together, and you never have two vowels together. And so that's how I remember which one is which. If that helps you, that's great. If it doesn't, then just ignore that last few moments there. Another thing that I want to point out here is that glucose specifically here is called a pyranose ring. And a pyranose ring is a generic term, and that just means it's a 6-membered ring that contains an oxygen atom. So all the carbohydrates in their ring form are going to contain these oxygen atoms. Now, I want us to look at what a 5-membered ring looks like. So D-fructose, this is when we have a ketone group here, and that ketone, we have the oxygen here and then the hydrogen here, and these come in and react, and we end up forming a ring here. This is a 5-membered ring, and that is called a furanose ring. So that's a 5-membered ring that contains an oxygen atom. Now, I want to point out that this is an example of a hemiketal group because it's formed from the ketone here, And so this is where we end up with that hemiketal. I want you to notice again, we're looking at the OH. When the OH is down, that's alpha, and when the OH is up, that's beta. Unlike before, where we had a hydrogen here, now we've got a larger group, but we're still looking at those OH groups. But these are examples of hemiketals. Now, when we go through and draw these, when you do this, for example, if we've got C double bond O, CH2OH, this is our friendly D-galactose. And so if we were to go and set up to draw these, what you would want to do is you would want to first kind of number your carbons. And so the way that we would number these would be, and I left out a hydrogen here, don't be me. The way that we would number these would be 1, 2, 3, 4, 5, and 6. Then when we go through to make our ring, the oxygen is on the back here, and that oxygen is attached to the number 1 carbon. And so that's that number 1 carbon there. And then what we do is we draw the rest of the structure like this. Okay, making sure to kind of darken this bit here so that it's coming out towards us. Then we go through and we number, right? 1, 2, 3, 4, 5, and then we would see the CH2OH, that very last carbon, number 6, up here at the top. And so then we would go in and we would fill in our OHs. And so we would come here and we would say, there's an OH here in the 4 position, and there's an OH here in the 3 position. Then in the 2 position, there's an OH here. And so I want you to notice that when we draw these, on the 3 carbon and the 4 carbon there, that they are on the left side, and here they are up. And then on the 2 carbon, it is on the right side, and there it is down. Now, on this anomeric carbon, when we draw it, remember, because that's the carbon that forms, you can have 2. You can have an OH that goes up, right? Or you can have an OH that goes down. And so if we were to draw the other anomer of this, it would look like this, where this guy is up and this guy is down. And so the one that is up is the beta, and so that would be beta D-galactose. And the one that is down is the alpha, and that would be alpha D-galactose. And so this is how we can draw from a straight chain like this to a cyclic Haworth projection like that. Now, let's talk about some of the reactions that we see with these monosaccharides. We learned in chapter 14 that aldehydes and ketones that contain an adjacent OH group are oxidized by an alkaline solution of Benedict's reagent, which is copper 2+. And so what happens is open chains of monosaccharides exist as aldehydes and ketones. And so these are readily oxidized. And so that means they are considered to be reducing sugars. And so a reducing sugar is just a sugar that can be oxidized by weak oxidizing agents. All right? And all monosaccharides are reducing sugars. So this means when you put a reducing sugar in a test tube with Benedict's reagent, which is the Cu2+, which is blue, that is going to go through a reaction and you're going to get an oxidized compound and Cu2O, and that is going to be kind of that red-brown color. And so here is an example of that. So we've got 4 test tubes, and this is Benedict's solution, and then this is maltose, which is a monosaccharide. So we have a monosaccharide there. We've got sucrose, which is a disaccharide, and then we have another monosaccharide here. And you can see when the Benedict solution is added that both the monosaccharides, the maltose and the lactose, react, but the disaccharide doesn't. And so that means that disaccharide is not a reducing sugar, and it remains unreacted. So this is similar to what we saw before. Now, other things that we can find here with our sugars is the hydroxy group of monosaccharides can behave as alcohols and react with acids to form esters. And specifically, they'll react with the phosphoric acid here and various monosaccharides found in cells, and give 2 kind of structures here that we would see fairly frequently if we were looking at some biochemical pathways. And then finally, when we talk about monosaccharides, these can react with alcohols and form what's called a glycidic linkage here. When we talk about a glycidic linkage, this is just a new carbon-oxygen-carbon linkage or bond that joins the components of the glycoside to the ring. And so these are example of glycosides, and we can see that here would be our new glycosidic linkage, because whereas we had an OH before, we now have a carbon-oxygen-carbon bond. And one of the things to kind of be aware of when we talk about these glycosidic linkages is glycosides do not have open chain forms. And because of this, they will not react with Benedict's reagent. And so then they are not reducing sugars. So We have talked about all of the different types of ways that we can look at monosaccharides. We've looked at the long Fisher projection form, and now we've looked at the cyclic Haworth projections. In the next screencast, we are going to talk about some common monosaccharides that we see and some details about those. And as always, if you have any questions, please feel free to stop by my office.